Hello, I am Khaja asifullah, lecturer in chemistry from Government Degree College, PLANCK'S, Hyderabad, Telangana. Today, in this session, we will take a lesson from chemistry, that is atomic structure. It's a part 2 or second lesson. Before this, I gave you one, so it is part 2 or second lesson. We know that in Bohr's theory, which says that electrons revolve around the nucleus in definite circular orbits, which are stationary because electrons revolving in those orbits are energy shells, do not radiate energy. If they do so, they will jump either to higher level or lower level. If they gain energy, they will jump from lower orbit or energy level to higher. If they lose energy, they go back to lower levels. In this way, we quantized energy. Every electron which is absorbing or emitting energy can do so in the form of energy packets called as photons or quantum. One more quantization principle is there, which quantizes the angular momentum, which says that MVR, that is angular momentum of an electron revolving around the nucleus in an orbit, circular orbit, is given by NH by 2 pi. There are few defects in Bohr's theory. To overcome those defects, we need to take certain phenomena, or we have to understand certain phenomena like black body radiations, photoelectric effect, Compton effect, de Broglie equation, and Heisenberg's uncertainty principle. To understand those things, we need to know about electromagnetic radiations. Then what are these radiations? They are defined as energy or radiations which travel with the speed or velocity of light, that is 3 into 10 to the power 8 meters per second, or 3 into 10 to the power 10 centimeters per second, or 3 into 10 to the power 5 kilometers per second, and which have oscillating electric field E bar and magnetic field B bar, which are perpendicular to the direction of propagation of wave. These type of radiations are called electromagnetic radiations, and in short we say EMR. This picture shows you the representation of EMR, how to represent an EMR or electromagnetic radiations on a paper or board. We had to consider 3 dimensions, means X, Y, and Z directions are X, Y, and Z axis. In one of the axis, let us say it is X axis, we take direction in which the wave is propagating. Which wave? Electromagnetic radiations. You know that energy has wave nature and particle nature. According to few scientists, they say energy has wave nature like hydrogen, etc. And some say that it has particle nature like Newton, etc. So if we consider it as a wave now, the direction in which it is propagating is given by this arrow, which is actually x-axis. And according to the definition, there are two oscillating fields. One is electric field, the other is magnetic field. So we need two more axes. Let the y-axis represent electric field. Now these axes naturally will be perpendicular to each other, or making 90 degrees of angle with each other. So red line or red axis represent electric field. This is the wave from this point to this point, one wave, and this point to this another wave as electric field. Whereas blue color, this axis is nothing but z axis, and this z axis represent the magnetic field from this to this, one wave from this point to this point, another wave in this way. This figure contains two waves, one wave, two second. Anyway, this is the definition and representation of the EMR, or electromagnetic radiation. Now, one more term we have to be familiar with is spectrum. After EMR, we have spectrum. What is spectrum? It is nothing but group of wavelengths or group of frequencies. So wavelength group or group of frequencies is defined as spectrum. Generally, spectrum is recorded in the form of lines or bands, etc. So it is just like a graph having lines, etc. Sometimes curves, whatever it may be. This is nothing but because of energy. It is the energy either absorbed or emitted by molecules or atoms, etc. So the spectrum is of two types. One is called emission spectrum. It is because energy is emitted, and the other is absorption spectrum because energy is absorbed. Two more types are like this: line spectrum and band spectrum. Generally, atoms give line spectrum, means the spectrum we get from atoms are like lines, whereas molecules give band spectrum. Band is again, it consists of closely packed lines. So under high resolution microscope, we can see the lines in the band. Anyway, next to it is electromagnetic spectrum. After understanding about the EMR, that is electromagnetic radiations, now we will take electromagnetic spectrum. What it contains, what actually it is. It gives you energy of different regions. We know that very small portion of energy is visible to our naked eye, which is called visible spectrum or visible region. So visible region is very small region of energy or electromagnetic radiations which is visible to our eye. Okay. Beside this, it contains regions like gamma rays, X-rays, ultraviolet rays, whose energy is greater than the visible rays or visible region. And there are few regions in this which has less energy than visible, called as infrared, far infrared, microwaves, radio waves, etc., etc. Few among them we have given here. All these are represented in electromagnetic spectrum, and one after other, and there will be no gap between the energies of two regions. They will overlap each other. Just is shown here as shown in this. Okay, actually these colors are given for regions which are above the visible, below the visible. Otherwise these colors will not be given by gamma rays or X-rays or ultraviolet rays, because these rays cannot be seen with our naked eye. Our naked eye is not sensible to this. This is color image, but you don't think try to understand in this way. These are invisible for us. So this portion is gamma rays up to this, then X-rays, then ultraviolet rays, then visible rays, microwaves, radio waves, etc., etc. Now, if you take this figure, this is the wavelength and frequency, wavelength in meters and frequency in hertz. Okay, so the frequency of gamma rays is very high, whereas the wavelength is very less. So the magnitude of wavelength of gamma rays is very, very less, whereas that of frequency of the gamma rays is very high. Why? Because energy is directly proportional to frequency. So as energy increases, frequency increases, and lambda or wavelength is inversely proportional to energy. So as energy increases, wavelength increases. So the shorter is the wavelength, more will be frequency and more will be energy, and longer the wavelength, lesser will be energy in it and lesser will be the frequency. So if we take the electromagnetic spectrum, gamma rays, then X-rays, then ultraviolet rays, visible region, infrared, microwave, radio waves, etc., etc. Their energy decreases from gamma rays to radio. Their lambda increases from gamma to radio, whereas frequency decreases from gamma rays to wave and radio waves. This is from left to right. The previous figure, previous two figures were from right to left. Now we have gamma rays on the left, so energy decreases from left to right. Frequency decreases from left to right, whereas lambda increases from left to right. Here we have this region visible. Actually, this figure gives you correct information. Here, this region only is seen by us or our eyes. All colors are in between here. This is violet and this is red. Between these, we have big GR, violet color, indigo color, blue color, green, yellow, orange, and red in this way. we have 7 colors, and this spectrum of visible light are white light. Now, after understanding all those things about electromagnetic radiations, etc., let us come to our topic mainly. This is the main topics now. These are the main topics. First one is black body radiation. What is a black body first? This type of body is called black body, and it is two-dimensional figure. In three-dimensional figure, it should be a sphere, a hollow sphere, a hollow sphere with a small hole in it. Okay, it is a sphere generally made up of platinum. Okay, black actually black sorry, definition of black body is actually a body which absorbs all incoming radiations. Okay, that is called black body. If light is absorbed by a surface, we get different colors, but when light is reflected back totally, it looks like white. If light is totally absorbed, it looks like black. So a black body or a perfect black body is one that absorbs all incoming light and does not reflect any. At room temperature, such an object could appear to be perfectly black. Hence, the term black body is given to it. Okay. Now, this is one of the object which may be treated as or considered as a black body. It is made up of platinum. Inside surface is coated with black, carbon black or lamp black, like that. And there is this sphere is hollow sphere, and there is a small hole here, and opposite to that there will be some projection here. As a result, when light or any radiations are entered, they undergo many reflections. They will not directly go back. Instead, they undergo many reflections. These reflections are because we will be having here a projection, cone-like projection here. As a result, there will be many reflections. As a result, all these radiations are absorbed here, and when they emit radiations, that will be in all regions. This is a plot of radiations given by a black body, and this plot or a graph or a curve is between the energy emitted and the wavelength. At different temperatures, this was recorded. We have two terms: energy, which is taken on y-axis, lambda, that is wavelength, on x-axis. Now, these are actually isotherms. Right? Why? Because temperature is constant throughout the recording of a particular graph. Here, this blue color graph was recorded at 1500 K or 1500 K. This peak is very low, and it is flat curve. When temperature is increased by 500 Kelvin, the peak is increased and the flat is less flat is the curve. Still more temperature, the peak is high and flatness is less. And one more thing, this dotted portion or line shows that the peak is shifting towards the left side. The peak here is shifting towards the left side, giving an idea that as temperature increases, the energy increases. Why? Higher the energy, lower will be the wavelength. Just now I told you, to understand this only, I explained you those things which in the beginning of the lesson we dealt. Here the peak is shifted from this point or this second point to nearly first point. From here, if we drop a perpendicular, this first point. From here, if we drop a perpendicular, this point. So this was a shift between the temperatures. Okay. In this way, we have to study the graph of the black body radiations, or this is the energy given out or radiated by a black body radiation. Again, this graph, similar graph it is. Now you can clearly see this is energy in kilojoules, and this is the lambda in Nm, and this is the graph recorded at T is equal to 3500 degrees centigrade. The next, this is black color, this is 4000 recorded at 4000, and this dark blue at 4500, green at 5000, and red at 5500. If you see this, the peak is about 6788 to 900 nm. In the case of temperature at 3500 K. Now if you consider 5500, it is here. So again we can say that the peak is shifted from this point to this point, or the peak shifts from right to left when temperature of the black body is increased. So it will radiate more energy. Again, the same graph can be seen. As I told you just now, this region contains more energy than this. Why? Because beyond this we have ultraviolet, X-rays and gamma rays. On the left side of the violet color, we have ultraviolet, X-rays and gamma rays, whose energy is much higher than the visible region. Whereas this is red region or red color. Beyond this we have infrared, far infrared, microwaves, radio waves, etc., whose energy is less than this visible region. And the visible region starts from this point to this point. And you can see that all colors are overlapping. There is no gap. So in EMR spectrum, there will be no gap. It will be continuous spectrum. So spectrum can again be divided as continuous and discontinuous. So it is continuous spectrum. Now the energy is more here. So we can say as the temperature of black body is increasing, the peak is shifting from right to left, means from less energy to higher energy. Okay. From the above, it is evident that the peak of the curve E versus lambda. This curve was between energy and lambda. So it shifts towards left. First point. Second point, indicating that E proportional to 1 by lambda means energy is inversely proportional to wavelength. Here E is energy, lambda is wavelength. So there is inverse proportionality between energy and wavelength. Generally, wavelength of a radiation emitted by a hard body or black body is inversely proportional to its temperature. First thing, the energy is inversely proportional to lambda. Okay, and wavelength also inversely proportional to this. Means as temperature increases, energy increases, and when energy increases, lambda decreases. In this way, we can say as temperature increases, lambda decreases, or if lambda increases, temperature decreases. After black body radiation, let us consider Planck's quantum theory. This theory is applied for radiation or energy. This is also called as quantization of energy. According to Planck, Planck is scientist. According to him, if there are two different energy levels, E1 and E2, such that E2 is greater than E1, that means second energy level is greater than first, then their energy difference will be given as delta E. The difference in E2 and E1 is given as delta E, and it is given by h nu. Therefore, delta E is equal to E2 minus E1, which is equal to h nu. Here, h is called Planck's constant, and nu is the frequency of radiations which are either emitted or absorbed by the body. And E1 is first energy level and E2 is second energy level. Here E2 should be there. So E2 is second energy level and E1 is first energy level. And the difference delta E is again equal to h nu. So the frequency is the main thing here. Why? Because h is constant. So constant will not play any role. Only frequency will play the role in the energy which is given out or taken in, because it is energy. If a body is in first energy level and if it absorbs energy, then it will go to second energy level. If it is in second energy level and emit energy, go to first energy level. So the energy difference or energy given out or taken in will be in the form of h nu, and its energy depends on frequency. And what is h nu? H nu is called quanta or photon. So energy is absorbed or emitted by a body in photons. This we can also write it as nh nu, where the small n can be equal to 1, 2, 3, etc. A number. Okay, 0, 1, 2, 3. If 0 is there, this whole will become 0, means energy is neither absorbed nor emitted. Okay, if it is 1, we can say 1 photon or 1 quanta is absorbed or emitted. 2 photons, 3 photons, like that. A Planck equation. This E is equal to h nu or delta E is equal to h nu is called Planck equation. And this quanta or photon gives you the energy, okay, or quantity of energy which is absorbed or released or emitted. This is called quantum energy or a photon. Here h is called Planck's constant and its value is 6.26 into 10 to the power minus 13 joules second. Okay, the units of energy are joules or kilojoules, or similarly calories, and it can also be given in electron volt for bodies like electrons, etc. So this is, when expressed in electron volts, will be equal to 4.136 into 10 to the power minus 15 electron volts second. Now this nu is frequency, and frequency is represented by nu or sometimes f and sometimes n also, small n. Therefore, if it is expressed by f, then it will be h into f or hf. Whatever be the symbol used for frequency, the energy is product of frequency and Planck's constant. As I told you just now, it is equal to point r photon. So energy of photon depends on value of frequency. Therefore, E is equal to h nu. Because h is constant, so we can say E is directly proportional to frequency. E proportional to nu. Here direct proportionality is there. In the case of lambda, it was inverse proportionality. Therefore, I said that energy increases as wavelength decreases. Here it is not the case. Here energy increases as frequency increases and energy decreases as frequency decreases. So for higher energy, frequency will be more. So here E is equal to h nu is called Planck's equation, because nu is given by c by lambda. Nu is frequency, c is velocity, and lambda is the wavelength of energy wave. So if we substitute this, we get E is equal to c by lambda. In place of nu, we are substituting c by lambda, or it is like this. Because c is constant, therefore again if you go back, you will get E proportional to 1 by lambda. Why c is constant? C is the velocity of light. Or electromagnetic radiations. All magnetic radiations will have same velocity, and that is 2.99 into 10 to the power 10 centimeters per second, or it is about 3 into 10 to the power 10 centimeters per second. Now we can write it as E proportional to 1 by lambda. Hence, according to Planck, an atom or molecule can absorb or emit energy in quanta or photon. Therefore, h nu is generally called as photon or quantum. Now, the next topic is photoelectric effect. What is photoelectric effect? The photoelectric effect is defined as the emission of electron when EMR, that is electromagnetic radiations, including light, hits a material, surface of the material or material, then electrons are emitted from the surface. This is the surface of the material, or mostly we say metal like cesium, etc. So this is the process called as photoelectric effect. Now this phenomena is commonly studied in electronic physics and in quantum chemistry and electrochemistry. So in both physics and chemistry it is useful, therefore we have to understand it clearly. In quantum chemistry and electrochemistry. Here in this particular chapter called as atomic structure, why we are studying all these things is to understand the nature of electron, because even Bohr could not explain the structure of atom completely. Therefore, we are trying to understand another theory of atom or model of atom called as quantum mechanical model. To understand that, we need these things. So quantum chemistry comes there. Now As I told you just now, photoelectric effect is the effect in which few radiations are concentrated on the surface of a metal like cesium or any alkali metal. Then we see that few electrons are ejected or removed from the surface of the metal. Here these are electrons. These electrons are called photoelectrons, but they are similar to normal electrons which are present in the atom. The other meaning is when we give certain radiations to the surface of the metal, these are incident radiation, means they are concentrated, they are coming or they are absorbed. Okay, and there will be scattered radiations also. Before going into next figure, let us understand this figure once again. This is the metal, or the this is metal surface. Here electrons are shown so that we can understand the process. Actually electrons are invisible to our eye, but when certain incident rays are concentrated or these are absorbed by the metal, electrons from the surface will be ejected or removed. Okay, next figure, let us consider this figure which can illustrate further. Now this is the surface. This circle represent the surface of the metal, this one. And here incident rays in the form of photons are coming. Okay, here photon or energy or quantity of energy is considered or taken as wave, not as a particle. You please remember that. Here, the energy is in the form of wave. It is taken in the form of wave, not in the form of particle. This photon, when is concentrated here, or incident light or radiation, what happens here is electrons are removed. But something is there. This is called scattered photon. Okay, this is again energy. But these two energies are different in value. They have different values. This is higher energy. This possesses less energy. Means the wavelength of this wave is less and the wavelength of this will be more. And this electron is moving. When it is ejected, it will move. This photoelectron will move in this direction. They will move in two different directions, making two angles with normal or this line. This is theta, this is phi. Electron is making angle phi, and the ejected photon or scattered photon is making angle theta. Ejected electron angle phi and scattered photon theta. Now what I want to explain you is this energy which is there in incident photon is actually equal to the energy of this photon plus energy possessed by this electron. So the sum total of this energy is equal to energy of this scattered photon plus energy possessed by the electron. Again, this will give you same illustration. So let us consider next figure. Here again the same as first figure was explaining or illustrating, the same thing here. In these are incident rays or incident photons which will strike to the surface of the metal, and I told you metal will maybe mostly it is cesium or any alkali metal. This is the surface from where the electrons are ejected. But again the same thing here is shown in different type of figure. Now let us consider this equation. Okay, this is photon. Actually this is the photon which is incident photon, or the photon in incident radiation. It is called energy absorbed or absorbed energy, and this is the other energy which is in scattered photon. This photon will also have certain amount of energy. Both the photons will have certain amount of energy, but as this is incident, it will contain more energy, this will contain less energy. This is called threshold energy. What is threshold energy? This photon should possess at least or minimum to this energy, so that the electrons are ejected from the surface of the metal. Otherwise, how many photons are striking the surface of the metal, no electrons will be ejected from the surface of the metal. So to eject an electron, the energy of this photon, which is incident photon or energy absorbed, should be more than the threshold energy of the electron, which is given by h nu 0. H is constant, so both are same. Nu is greater than nu 0. This is nu 0, which is less than nu, or nu is greater than nu 0. Means energy depends on frequency, therefore it has higher energy than this. So every metal has its own threshold energy. It depends on metal only, and the photon, which is called incident or striking, should possess greater energy than this threshold energy. So it is, our threshold energy is defined as, it is the minimum energy required to remove or eject an electron from the surface of a metal like cesium or any alkali metal. Now, the ejection of electron from the surface of a metal like cesium due to electromagnetic radiations is called photoelectric effect. Now, the next thing we have to understand is, what is this nu 0? Here we are mentioning that it is threshold energy, and it is also called as work function. H nu 0, or it is a photon, is equal to work function. And the remaining energy, because threshold energy is less than the photon, then where the other energy has gone? These two energies should have been same, but it is less, it is more or greater. Therefore, this energy is sum of work function and the kinetic energy of electron which is ejected. Just you take, or again you see this, it has some kinetic energy, because this every moving body, it is electron moving in this direction, will possess some kinetic energy, and this scattered photon again contains certain amount of energy. Therefore, the sum of these two is equal to the energy of incident photon. Okay, and the kinetic energy possessed by the electron is given by half mc square. Kinetic energy is given as half mc square, where m is mass of the electron and c is velocity of the electron, and 1 by 2 mc square is called kinetic energy. It is the formula of kinetic energy, or to find kinetic energy we can use this. So this is the kinetic energy possessed by the electron which is ejected, or ejected electron from the surface of a metal like cesium. So we have, let us summarize this, called as the effect, which is called as photoelectric effect. It is nothing but the emission of electrons, when emission of electron from the surface of any alkali metal like cesium, when electromagnetic radiations are concentrated on the surface. Okay, so that electromagnetic radiation may be light, because visible region light is part of electromagnetic radiation. This phenomena is called photoelectric effect, and it is useful in chemistry also, as well as in physics. So the incident photon will have certain amount of energy in it, and this is the sum of the energies having by these two things. One, photon which is scattered, and the other is the energy of electron which is ejected. Because this energy is utilized, therefore this energy will be less than this, and this will be equal to the sum of these two energies. And the energy of photon again can be given as h nu only. To differentiate, this is given by h nu and this is given by h nu 0, and the kinetic energy of the electron is given by half mv square rmc square. Why? Because every moving body will have certain kinetic energy, and this energy is less. Therefore, where that energy has gone, the difference is gone. So the difference of energy is this energy only, which is nothing but the kinetic energy of the electron ejected from the surface of the metal. This is the photon hitting the surface of the metal, due to which this electron is ejected or removed. But one thing is clear, that this energy, the photon should contain more energy than this energy, which is called threshold energy of the photon electron ejected. Until unless it has higher energy than threshold energy, electrons cannot be removed or ejected. If less amount of energy is concentrated, no electrons will be ejected. Now, this is a graph which shows that what we have said just now. It should have, that means incident photon should have this much energy. It should be greater than this point, and this point on this axis we have taken it in the form of frequency, energy in the form of frequency. Why? Energy E is equal to mc square or h nu. So E depends on frequency. So we have taken frequency here in hertz. So this is the point. Before that, no electron is ejected. Okay, up to this frequency of radiation, no electron is ejected from the metal. Only after this point, means the photon, incident photon, incident ray or incident photon should have energy more than this. More than this means, from this, if we calculate the energy in frequency, this is about 4.4 into 10 to the power 14 hertz, or exactly 4.3 into 10 to the power 14 hertz. So this is called the threshold energy, or the frequency nu 0 of threshold energy. Okay, this threshold energy. What is threshold energy, or by which symbol it is given? H nu 0. H is Planck's constant, 6 into 10 to the 6.6 into 10 to the power minus 34 joules. The frequency nu naught or nu 0 is this much. So until unless it has this much energy, no, it cannot, or it will be unable to eject the electron. So let us stop here, because we have dealt with photoelectric effect, Planck's theory, etc., which will be useful in understanding the quantum mechanical approach to the model of atom. So let us stop here. Thank you.